Alright, 7.2 Logarithmic functions and their graphs. Definition of a logarithmic function with the base A. So before I tell the definition, a little background. Main purpose of logarithms is to help us with exponential functions. It's another way of writing exponential functions. Okay. There are times when we have exponential functions with unknowns in our exponent. And that makes it hard for us to solve equations. Logarithms help us do that. It helps us solve equations with unknowns in the exponent. Okay, definition time. Let a be greater than 0 and a not equal to 1. Similar to our exponential function. For x greater than 0, y is equal to log base a of x if and only if x is equal to a to the power of y. What matches up here is the base of the logarithm is the base of the exponent, and then the exponent is whatever the logarithm is equal to. Okay, so it's a way to know how to match them up. And then, of course, whatever the big number is of the logarithm, that's what the base and the exponent are equal to. And it's written in function form of f of x equals log base a of x. That's how you say it. Log base a of x. That's how you say it. Okay, that's how you say logarithm. Hopefully you know that by now, but just a reminder, that's how you do. Alright, a few quick examples here. The one down below here is the easiest. I'm going to do the one at the bottom here. So we write this in exponential form. We have 3 to the power of I don't know equals 27. Now, what value of x would make this true? 3 to what power will make it equal to 27? 3 to the power of 3. Because 3 times 3 times 3 is 27. So that's what the answer would be. X is equal to 3. Next easiest one, top left. Some might argue that it's actually the easiest, but we'll go roll with it. So 5 to the power of x equals 1. Remember, wherever the base is gets the exponent. Just a little reminder. So, what does x need to be equal to? So it's equal to 1. Well, anything to the power of what equals 1? 0. So x is equal to 0 would be your answer. Now, last one. The one that might be the most difficult. 8 to the power of x equals 2. Now, in cases like this, try to think of your radicals, right? So square root of 8, you can't find square root of 8, unfortunately. And that definitely doesn't equal 2. The third root of 8, though, is 2, right? So the third root is just like saying 1/3 power. So your answer is x equals 1/3. All right, here are the properties of logarithms. There's 4 of them. So hope you read them. For the first 2, here are the rules, and it's because of these 2. You kind of saw those in the examples before, except for this one right here. If this and this number are the same, it's equal to 1. Log base a of 1 will always be equal to 0, all the time. Here are 2 special rules right here. Anytime the bases are the same, you have an exponent to the big number for the logarithm, it's always going to be equal to the exponent. And also, if you have a to the power of a logarithm with the same base, as in this base and that base, it's whatever this number is right here. And also, if 2 logarithms have the same base, you can set them equal to each other and solve. Also, one thing is I should mention, if you hear the word common logarithm, that means any logarithm with base 10. We usually don't write 10, we just write log, and you're good. Alright, 2 quick examples to use our properties. Log base 7 is 7 to the power of 5. Since the 7s match up, your answer is just 5. Nice. And then for the second one here, since the bases match up, your answer will be whatever this number is, which is 21. Easy as that. That's all you have to do for the property problems. Alright, so let's do some graphing then, shall we? So we have h of x is equal to log base 4 of x minus 3. So let's pick some points. And let's also change this to exponential form. Yeah, I know there's no y's. I put y as the output. So it's 4 to the power of y equals x minus 3. So when y is equal to 0, what does x need to be equal to? If y is equal to 0, that makes this whole left side 1, and x will need to be equal to 4. If y is equal to 1, what does it tell you? If y is equal to 1, that means x must be equal to 7. If y is equal to 2, so 4 to the power of 2 is equal to 16, and that means x must be equal to 19. And let's plus a point, so 4, 0, 7, 1, 5, 6, 7, and 19, so it's going to be way over here. Now what's going to happen after we hit that x-intercept? Well, with the graph of the logarithmic function, if I were to pick y values that are negative, for example, let's say I pick negative 1. Negative 1 will be 1/4 on the left side, and I add 3 to it, so it'll be 3 1/4. So it would start to go down here and continue on, but it'll never touch x equal to 3. Never ever. Okay, it can't do that. X can't be 3 because this 4 to the power of y can never be equal to 0, ever. Okay, so that's what the graph looks like. You might recognize this graph a little bit, because if you turn whatever your device is to the side, it looks like an exponential function. Okay, and it is almost, except it's a logarithmic function. But it looks like that because it reflects. It reflects over the origin, which is pretty neat. Okay, excuse me, it does not reflect over the origin. Spoke, it reflects over y equal to x, the line. So it reflects right over that line. You don't need to draw that line, but the original logarithmic function reflects right over that line. Okay. In this case, it moves over a little bit because of our shift to the right 3 of our original function. So that's what the graph looks like. So let's talk about some other things like domain and range. What's domain? Well, domain can't be anything less than 3. It can't include 3, right? So it'll be 3 to infinity. Range, even though it doesn't look like it, it will hit every y value eventually. It may take a long time, but it's going to be all real numbers. Negative infinity to infinity. It is always increasing. And it's continuous. And we have a vertical asymptote at x equal to 3. Okay, no horizontal asymptote, just a vertical asymptote. And our x-intercept's at 4, 0. No y-intercept, we have an x-intercept. If you might notice from whenever we were graphing exponential functions in the last section, it's pretty much the same thing, except some of the things are flipped. Instead of having a HA, we have a VA. Instead of having a y-intercept, we have an x-intercept. Things like that, we kind of flip. Instead of having a domain of all real numbers, we have a range of all real numbers. Alright, then we have something called natural logarithms, okay? Anytime we have a log with a base e, instead of writing log base e, we can write ln instead, okay? And we call that the natural logarithmic function, this right here, okay? X also cannot be negative or 0, or it doesn't exist, okay? So, natural logarithm right there. Here are the properties of natural logarithms, very similar to logarithms before. Go draw them down. These first two, as before, are true because of this right here, okay? So this is just kind of an explanation as to why this is always true. And the others should look very similar to your other logs, properties that you wrote earlier. They're just with ln and base e. Let's do one quick example. Let's say we have ln of e to the power of 12. What's it equal to? Well, if you look at rule number 3, we know it's going to be equal to 12. Okay. Anytime we have ln of e, wherever that exponent is, that's your answer. Okay. I appreciate you watching, and we'll see you in class.